Good afternoon, everybody, and thanks for coming to our last KEGS presentation before the summer break. For those that are online, this is Elizabeth Barani. I am filling in for Edna because Edna is currently in Gabon. Our presentation today is by Alan Reid. Alan attended the University of Zimbabwe, then he continued with his master's in geophysics at the University of London, continued here PhD in Canada at the University of Alberta. Then Alan taught applied geophysics at the University of Alberta and went back to Rhodesia, taught there. In terms of his industry experience, Alan joined Newmont Mining, and then Robertson Research, then GTech in Leeds, and now Alan is a consultant. Alan is extremely prolific in his knowledge, in presentations, in papers, and I'm sure you all know him very well, but I had to cover the bio. Right now we have about 238 people online. I'm just saying that so that you're aware what the audience sees. I would like to invite Alan up to make his wonderful presentation today for us.
It's a little overwhelming to have that kind of an introduction because it's going to be hard to live up to it, but I'll do my best. I'm glad to see so many old friends in the audience. It always makes it a little easier. Can I say that this is, for me, a big deal, this meeting. It's the first regular KEGS meeting I've ever attended. I've been aware of KEGS's existence since the mid-70s because the South African Geophysical Association, SAGA, was founded then explicitly mimicking KEGS at the suggestion of Rod Woolham, and I was a founder member. So I've known about KEGS for a long time. I was for quite a while a KEGS member. I'm not now because there seemed no point. I could never get to meetings. But I've finally gotten to one by offering a talk. So for me, this is kind of a wow. This presentation is a lot of elementary stuff, really. It's things people have taught me over the years where I thought I knew, and then somebody said, wait a minute, that isn't the way it is. So I'm sharing with you some things I've learned over a long time, and some of them are a little counterintuitive and perhaps not what is current practice. And really I'm doing this to see if I can't shake up a little thinking, and if it generates a little bit of a discussion afterwards, all the better. I've broken this down into forgotten truths, myths, and sacred cows because there's kind of three categories. Forgotten truths are things which undoubtedly are true that people tend to forget and therefore get in a mess. Myths are obviously things which lots of people in our profession believe but which are not true. And finally, sacred cows are things we all do without maybe thinking, and it's totally built in, and maybe we can do a little better. So now, 5 forgotten truths. I'm just skipping through them here, but I'll go into detail in a minute. One is the nature of the magnetic field. That there is as much negative anomaly as positive anomaly in any anomaly. I'd like to talk about undersampling and aliasing a bit. Effects of remanence and pole reduction, although you've had quite a lot of that from in the cloud, I guess. The whole business about the fact that really the models we use are maybe deceptive because geology doesn't work the way we make our models. Self-similarity I'm talking about. And finally, maybe a slightly surprising thing about the Bouguer anomaly. Then I've got for you 4 myths. One is that we should always traverse perpendicular to strike. The next is that Fourier and Bouguer corrections put the gravity station on the data. That the structural index is a real variable and may be used as a tuning parameter. And that a magnetic base station may be a lower quality than a rover. All of those are myths. They're all wrong. Sacred cows. I want to shoot down the Bouguer anomaly or have a go at it anyway. Or at any rate, make people think before they use the Bouguer anomaly. Bouguer anomaly should only be used with your braining gear. A lot of people do Fourier transforms on geographic grids. It's very naughty. All the information's in the profile. Yes, but no. Let's talk about TMI. It's a bum name for what we use. And I'd like to have a crack at 3D Analytic Signal as well. Right, getting down. That's quite a laundry list, and it hops all over the shop of gravity and mag. And maybe some of these thoughts are more appropriate to oil practice than minerals practice, but hey, let's not be proud. This is the only math I'm going to show in the entire presentation, so let's get it over with. These are Maxwell's second equation. Says the divergence of E is naught. What does that mean? Magnetic field lines form closed loops, or if you like, there's as much low magnetic anomaly as there is high, and that's always true. It's one of Maxwell's equations, and nobody has beaten Maxwell at that game yet. Put it another way, the mean value of a magnetic anomaly is 0. If it isn't, you're not doing it right. Just to illustrate it, here's the anomaly of a sphere seen with different degrees of inclination. And even in the one you're most familiar with, because you're in high inclination, that all this purple around here is negative, and we tend to ignore it because we all look for the, the kick. You know all about the kick. But look at we got all kinds of lows here. Let's not forget it. So please interpret the whole anomaly. Know what patterns to expect at any given inclination. Learn to recognize wrong patterns indicating remanence or anisotropy. Or if you can't do this just by looking, you shouldn't be interpreting mag. You've got to have this built in. And of course, as you know, what's right for any given inclination depends on that inclination. John Sumner at U of Arizona taught me all this quite a few years ago in the presentation he gave to SCG, and I'd like to acknowledge that. Aliasing. This is less of a problem than it used to be because thankfully we do fly closer than we used to. When I first started looking into designing an MAG survey, I asked around, and the industry standard was 1 kilometer for line spacing. And I said, why? And the answer was, because it's the industry standard. And when I said, why is it the industry standard? They just said, it is. Well, I'm glad to say that's no longer the truth. Anyhow, the point about this is if you sample too widely, you get nonsense. If you've got a signal that wiggles like that yellow line there, and you sample it where the green dots are, then you get the green-blue line as the result. And it doesn't look much like the truth. It's called aliasing. In order to avoid aliasing, you need to sample more than twice per interval. Now, we need to know what wavelengths might be present if we're going to apply this particular principle. And praise be, the answer was given to us by Spectrum Grant in 1970. It took me a while to recognize this. Now, I'm not sure Alan Spector yet recognizes the incredible importance of his own work. But anyway, there it is. If you've got a really good memory, these two pictures are engraved on it. And if they aren't, go and read the paper. You ought to know this one. Basically, it says if you plot the log power spectrum of a mag field regardless of azimuth, you will get a series of straight lines, depending on the depth. Please feel free to sit down and make yourselves comfortable. I exploited this in 1980 in a very short note, which was well received at the time. And I believe it's still definitive. This is a design diagram. If I may interpret it for you, if you'll accept 5% nonsense in your maps, in your images, then a total field map should have line spacing no more than twice your height above sources. If you're doing gradients, the line spacing, vertical gradients that is, your line spacing shouldn't be more than the height above sources. And if you want to do modeling, much the same. So there's a little design diagram. It's a very simple set of rules to remember that came out of a fair bit of mathematical grinding, mostly the work of Spector and Grant, a little bit from me. And here is the most beautiful example of it provided to us by Peter Hood in the Exploration 77 volume. This is vertical gradient data. On the left, we have something which meets the design criteria I just spelled out, and it's a reasonably well-constrained map. If we knock out half the lines, which is still a pretty darn good survey, it's clearly interpretable still. I mean, this fault here is obvious to any competent interpreter, isn't it? It's a pity it's not there. And if you knock out here, you're still not that wide, but you're in 80% alias power, and it's a lot of cowpats, isn't it? I mean, we call it moose pasture in the oil industry, so maybe it's moose pats, but you know what I mean. Beware of undersampling. Now, gravity is a bit more forgiving than mag, but gravity gradient isn't. So I need to acknowledge help with this from Peter Hood, Spector and Grant, of course, and Mike Schoenberg, who was the editor of Geophysics at the time, because when I submitted this paper, it was recommended for rejection by all reviewers and the associate editor. And the editor said, hang on a bit, you guys aren't thinking. Next forgotten truth. People tend to forget about remanence. And of course, it's a pity, because it does occur more often than you might think. This is an example, one of my favorite examples. It's from northern Namibia, where I used to work. Tsumeb mine, let's see, where's my cursor? Tsumeb mine is just off the map here. Tsumeb holds the world record for the most mineral species. It's an incredible mine. Combat down here runs 20% copper in some stopes. So this is economically valuable. Okay, this is topography, the top picture. And you can see there's a valley there with a flat bottom. And this is what the airbag looks like. There's a rather strange, largely negative anomaly. This is in the southern hemisphere, but at a kind of intermediate inclination. There's clearly something weird going on. Okay, that's the mag anomaly top again. Here's the RTP. It doesn't pole reduce very well, does it? It's all lows. Where's the highs? Obviously remanence. If we do the total gradient amplitude, which some people like to call the 3D analytic signal, we get this middle picture. Or if we do the total field anomaly sum of all components, that's a thing called T, published by Stavro, we get this. This one emphasizes the edges, this one emphasizes the body. This is something that I think more people should be paying attention to. The amplitude of the total anomaly. Here's some bounded eye information. I can't tell you where because it's proprietary data. Topography on the left, magnetic anomaly in the middle, RTP on the right. Well, it's a bit of a mess. Okay, total gradient anomaly in the middle. Well, we can see where the bounded eye information is now. Well, there's the T on the right. But you know, remanence is messing us around, or maybe it's anisotropy, but at any rate, not simple induced. So beware of remanence. It won't pole reduce. And can I introduce those of you who are not aware of it, just Stavro's total vector amplitude. He published a paper in Geophysical Prospecting 5-6 years ago. If you can't find it, send me an email. Now, Ian McLeod claims to have solved the pole reduction from the equator, and he certainly made a great advance lately. He reminded me of it this morning. It's still not quite there, but close. Now, this is something I think a lot of people don't realize, although Mark Pilkington at the GSC has published some good stuff on it. The crust is not made of a bunch of blocks. It's actually magnetized in a fractal way. So what we're saying is geology itself is fractal. This is what geology looks like. It occurs at all scales. And so we've got a geological map here, and here we've got under a microscope a bunch of mineral grains, and it's the same sort of structure. It's multi-scale. And it's not a bunch of blocks, you know, they're each 1 kilometer or anything like that. We don't have the mathematics to deal with this properly. There's been very little published. Some papers have been, but I think this is where the growth is. I think there are PhDs to be done here. But I'm not going to be supervising them because whoever does it better be mathematically aware, and so have the students need to be. Here's an example of exploiting this. This is a paper by Stefan Maus in 1999, published in Geophysics. It's a piece of Namibia here, the Omaruru Delta. But this is just desert here, and this is what the mag looks like. By the time he's turned it into depth abasement, which is near the surface because it's just covered with sand, he's actually been able to recover a paleo river channel. Well, I think it's awesome what you can do with this. It's almost certainly the best depth estimator I've seen. It doesn't matter maybe to minerals people, but to oil people, depth estimation is vital. So if all of this is new to you, I can help you get up to speed insofar as it's possible. I'm suggesting there's a paradigm shift we all need to think about. And the two people who published most are Mark Pilkington and Stefan Maus. This is one I had rammed down my throat quite recently. We were producing some maps, and a client said, the Bouguer anomaly should be negative and yours isn't. And it took me quite a bit of thinking, and eventually, okay, here's the Bouguer anomaly of Australia. Anything from yellow through green into blue is negative, and you can see basically it's true. Well, there's South America, same again. Did you all know this? Is this something that it took me all this time to find out? Bouguer anomaly is normally negative, below zero that is, in an absolute sense. It's true. And there's a reason. If you're onshore, there's positive topography, which means there's isostasy, and we tend to forget the isostatic effect. We should all be making isostatic corrections, especially in the oil industry, where we're dealing with big structures. In minerals, it maybe doesn't matter so much. All right, so much for the forgotten truths. Let's go at the myths. We all know that you ought to fly perpendicular to strike. It's obviously right, because it gets you the best sampling of the down dip. So it's obviously right, but somehow it's not quite right, because of course magnetic anomalies are not isotropic. For example, the whole of Tanzania was flown east-west because that was a perceived strike, and in consequence they missed a lot of kimberlites, which is maybe a bit of a pity. I was involved in a survey in Mali, a very big survey, which was originally planned to be flown east-west, because again the perception was that the geological strike was north-south. After a big fight and some blood in the streets, we got him to fly at 45 degrees. And what did we see? A whole set of east-west dikes that were previously unknown. Hey. Let's look at a couple of models just to make the point. Up above here, we've got a dipole at it's a sphere at an intermediate latitude with a high-low sort of as we expect. And here it's oversampled, so we're seeing everything. Here we're sampling it using the sampling rules I just spelled out, with one of the profiles going straight over the sphere. And we more or less get it. Here we're running them east-west with one of the profiles running straight over the sphere. Well, the picture tells its own story, doesn't it? And here we're doing one at 45 degrees. It's not great, but, you know, it beats this one, you know, the surprise baboon. Do you want to be a surprise baboon? Think about which way you fly things. This was taught me by Roland Smith at Shell, for what it's worth, because I knew for sure you flew across strike until he said, think again, pal. Well, it hurts when a client tells you, the consultant, you need to think again. And hey, try not fly more than 45 degrees from magnetic north. And this advice doesn't matter in Canada. You've got vertical mag fields here. I'm talking about intermediate and low latitudes. Fly whichever way you like in Canada. Next myth. Free air and Bouguer corrections move the gravity station to the datum plane. In other words, we observe data here, we do the corrections, and now the data points are on the datum. Who says this is the case? Well, some respected authorities. Telford says so. Nettleton says so in that particular book. Sheriff in the Applied Geophysics Dictionary says so. Then again, there are people who think the opposite, like Jung in Schwerkraft for Fourier, etc. There should be a T in there, my apologies. We all know Blakely. I hope you know about Jacobi and Smilder. It's an excellent book. Then, who also says it ain't so, but indirectly, Gaunt and West, you've got to read it very carefully and put this against that and think hard, but yeah, they actually say it doesn't move it to the datum, but they don't say it in so many words. You've got to look at it and think hard. And then who ignores the question? Well, Nettleton, Griffithson, King, Milsom, yeah. So what's the truth? The truth is that the free air correction removes a global effect on the Earth as a whole. The Bouguer and terrain corrections remove effects of local topo variation, but neither gives a downward continuation. So you need still to model with your points where they always were. Do we all know that? I mean, I hear from Jerry Conrad that he's battling this one all the time. So, next myth. This is one I battle because I'm associated with the structural index. And it's partly my fault or fault of myself and my fellow workers, because our original code, which is sitting inside the Geosoft implementation, allowed the structural index not to be an integer. So lots of people use whatever structure index strikes them as right. The models I'm showing here are relevant to Euler type things: spheres, line sources, thin bed faults, sheet edges, infinite contacts, and that's pretty much it. This kind of approach, this Euler type homogeneity approach, doesn't work well on thick things. So here we're looking at a thick step, and the point really is, if you're sitting here, it looks like it's infinitely thick, because compared to your height to the top, it is. If you're looking here, it looks like it's thin. That's a structure index of 1. And in between, it doesn't look like either. And as you move from one to the other, it changes. So the point is, if a structure index is not an integer, it's not a constant. But all our software assumes that it's constant, which is characteristic of the body. And I'm saying if it's not an integer, it's not a constant, which means both the software we use for this ain't right. There's a paper coming out in Geophysics because this is something Jeff Thurston helped me get straight. I guess you all know Jeff Thurston? You all know Jeff Thurston? Some of you know Jeff Thurston. Canadian. Well, I'm surprised. Should come out in Geophysics in the next few months. Discussion of what you can and can't do. Next myth. We all know that the magnetic base station need not be as good as the mag in the aircraft or the one you're carrying around. We can get away with a cheap one. Everybody knows that. But let's do a little bit of lab physics 101. We've got a rover signal, where's one, with an uncertainty of delta R and a base signal of uncertainty delta B. Then if we go and subtract the base from the rover, that's the uncertainty we're going to get. I got taught this in Lab Physics 101. I'm sure you did as well. If the rover is much lower noise than the base, then the noise in the system is the noise of the base. So for example, if you've got a rover signal of 35,003.21 nanotesla and a base signal of 35,000 plus or minus 1, the anomaly is 3 plus or minus 1. There's your problem. All the noise and uncertainty in the base translates into the difference. So there's two kinds of mag contractors, those who remember this and those who don't. I've run across both types. The leading Canadian contractors have this right. I'm not going to name names. Just find out who uses a decent base. Just ask them that. Some sacred cows. Why do we make Bouguer corrections? We make them so that our maps won't be dominated by topo effects and only show the geology. And that's great. I mean, sure. And how do we make a Bouguer correction? We all know how to do that. And is this a good idea? Well, sometimes for mapping. And is it okay to model it? Well, maybe. Here's a problem I was faced with a few years ago. This is actually Lake Edward in the East African Rift Valley. And we got basement around here. And as far as we can see, totally different rocks on the two sides, and a hell of a lot of topography. And here I actually modeled a Fourier because I didn't know how else to handle it. I didn't know what Bouguer correction to apply, given that the density this side is completely different from the density this side. How are you going to make a decent Bouguer correction? You just don't know. So I'm suggesting there is some sense in modeling the Fourier anomaly and putting the topography into the model. So you kind of do that Bouguer correction as part of the model. It's quite easy in 2D. It's challenging in 3D because, of course, you don't know the densities in the Bouguer correction layer. And that's the whole point. When you do a Bouguer correction, you assume constant density. And the first thing you come across is, hang on, I can't model this stuff because I don't know what it is. But we just assumed it was constant. Well, if you don't know enough about the geology to model between the surface and the datum, the Bouguer correction is wrong anyway. Now, there is a workaround. You don't have to model a Fourier. If you must model a Bouguer, please remember you've got to use the Bouguer density as the background value, which means you need to know what the Bouguer density was. And if you've got old data and the Bouguer density has been lost, you have lost a key fact, and you can't do a really good job. Next sacred cow. All the commercial software, Geosoft, Intrepid, you name it, is perfectly happy doing Fourier transforms on geographic grids. That's nonsense. Where do Fourier transforms come from? They come from the fact that if you solve Laplace's equation with separation of variables, you arrive at the Fourier coefficients. And if you solve Laplace's equation in spherical coordinates, you come up with spherical polars. Sorry, with spherical harmonics. You should be using spherical harmonics on that long. What we're saying, what we're normally doing if we do FFTs on that long grids, is that a flat piece of paper is the same as a sphere. Well, it's not fundamentally a good approximation. Basically, we're using a screwdriver to hammer in nails, and so the results might not be satisfactory. What problems do we get? Well, the X and Y scales are different, so your filters become anisotropic even though you thought they were isotropic. If you're doing an Euler decon, you get depths in degrees, but are those degrees latitudes or longitudes? You get curvature distortions. You get unpredictable results from physical filters like pole reduction. If you've ever tried to pole reduce that long grid, you might know what I mean, and if you didn't notice, well, it's okay near the equator provided you're not too far, too big an area. So I'm suggesting reproject if you can. If it's a big area, you might want to use Lambert's. Or, best of all, use spherical harmonics, but they're not available easily in commercial packages. If you want the justification for it, it's a paper by Fourier, which I think made me think. Next sacred cow. All the information's in the profiles. That's obviously true, because that's all the information we've got. But let's not process profiles as if they are only in count. If you process a profile on its own, you're making 2D assumptions. You're assuming that each profile crosses 2D geology. And geology is often not 2D. So things like continuation, gradient, pole reduction are all misleading. So beware, keep your brain in gear. Okay, finally, TMI, total magnetic intensity. We all know what we mean. And we don't mean total magnetic intensity when we say total magnetic intensity. What we mean is take the measurements, do some base corrections, subtract the IGRF, do a little leveling, and that's a TMI, right? Well, that's not the total magnetic intensity. A TMI is what we measure. I'm suggesting that this thing that we all produce, we should call the magnetic anomaly. It's got a mean near zero, and it obeys Gauss's law, or if you like, Maxwell's second equation. So we subtract the IGRF, and we don't add anything back, so that our maps have zero average. You know, a lot of people add 5,000 or 30,000 or something after taking off the pole reduction, or after taking off the IGRF. Why? Because it used to make it easier to hand contour. That's the only reason. Let's stick with the good physics. Take off the IGRF. Don't add anything back. Call it the magnetic anomaly. Now, it's been suggested we should call it the IGRF residual, and that's technically absolutely right. But it sounds kind of techy, doesn't it? Why don't we give it a name that suggests it's what we normally use? Finally, the 3D analytic signal. If I may remind you, Navigian published this stuff back in '72, although it's been suggested there was previous work published in Russian, and I'm not proposing to get into that debate here. In 1984, he published something entitled Towards a 3D Automatic blah, 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 but he avoided suggesting that the so-called 3D analytic signal was the thing. It turned out Roost, Verhoeven, and Pilkington did publish that suggestion back in 1992. In the meantime, Namibian has always insisted that the 3D analytic signal was an unsolved problem. We didn't have it. When you call something analytic signal, you are labeling it with a whole lot of very interesting physical and mathematical properties. The term analytic signal has a mathematical meaning. We are not free to call anything we like analytic signal just because it's convenient. It's like calling yourself president of the USA when you're not. You do not have that right. And people, I'm suggesting we shouldn't do it. Just recently, Namibian has told me that he has proved to his satisfaction that it is not possible to generate a 3D analytic signal. I don't know if he proposes to publish it or not, but I'm mentioning it here. So I'm suggesting this thing, which we tend to call 3D analytic signal, should be renamed what it actually is. The total gradient amplitude, if you want a three-letter acronym, TGA. And stop calling it 3D analytic signal because it's not. And could I also suggest people think about using the total vector amplitude, T, proposed by Stavrev? I think it's very useful. And you've seen these pictures before, but it's just demonstrating total gradient amplitude and T and the magnetic anomaly. In a case where remanence is getting in the way, they still both give you something useful. So, lots of conclusions, rather more than 6, but magnetic anomalies have lows and highs. You should sample closely enough. You should avoid east-west flying. You should be aware of remanence. You should think fractals, not blocks. You should use a good magnetic base station. You should work with magnetic anomaly, not TMI. You should work with total vector amplitude or total gradient. You should use structure indexes that are integers. You should project geodetic grids before you do FFT work. The Bouguer anomaly onshore is negative. You should think about modeling Fourier gravity, and maybe you should use the isostatic residual. These are all my tutors. They are an illustrious bunch. If you haven't heard of most of them, you need to go check them out. These are people who have made a difference. They made a difference to me. They should make a difference to you. A fair number of them are Canadians, incidentally, which is as it should be, but they're not all. So I have a challenge for you now or any time in the future. Think of some more sacred cows that need slaughtering. The end. If I might suggest, for the sake of being fair to the online audience, we might take questions in turn from the flesh audience and the online audience. Do you have a lot of questions there or not, Elizabeth?
I have a couple.
Okay. Questions, comments, fisticuffs, I don't mind. Someone who said, hey, I don't agree with you, this is crap. Let's hear it. Chris.
I'll throw out another sacred cow, terrain correction. It's similar to your Bouguer correction, but terrain correction.
Chris is suggesting that another sacred cow is terrain corrections, but I'm not sure in what way you distinguish it from Bouguer. I was including terrain corrections in the Bouguer.
Okay, fair enough.
Same arguments apply. Questions from you, Elizabeth?
Akram Aziz says, negative readings in Bouguer?
Akram Aziz says negative readings in Euler. Akram, I don't understand your question. Would you mind resubmitting it in another form so that we can try and answer it? Do you mean negative structure index? If you do, I can answer that, but can you confirm that that's what you're asking about? And then if it is, or anybody else wants to know about negative structure index, I can talk for hours on the subject. Any other comments here? Okay, Elizabeth, you have any more?
Yeah. Thanks for the presentation. Sometimes we don't know the strike of the. Thank you everyone for attending. So I suppose the question is we don't know the strike.
And what should we do? Yes. And indeed, that is the whole point. We often don't know the strike, and that's why we should not use east-west because we think it's the strike. If you don't know the strike, there's a good reason to fly north-south. If you do think you know the strike and you want to bias it, by all means bias it, but don't go beyond 45 degrees from north-south, in my view. And I know a lot of people who think different, but I'm suggesting it.
That was Roberta Dedotti.
That was Roberta Dedotti. Okay, question from here.
Yeah, and my question is, you said avoid to fly east or west. That's only for the long magnetic latitude. How about in Canada? We're high magnetic latitude, and but they may have some remnant.
Okay, the question is, what about Canada when it comes to what direction you fly? In my view, in Canada, you may as well fly perpendicular to any structures you know about, and it'll cause you very little problem because you're in high latitude to a first, or because you've got the magnetic pole in your own backyard. Canada owns the magnetic North Pole. Your data here are close to pole reduced already, so that anomalies from isotropic sources will show up isotropic. And so this whole question of the fact that mag anomalies at intermediate and low latitudes are anisotropic does not apply. At high latitudes like here, high magnetic latitudes like here, my point is irrelevant. Fly whichever way makes sense to you. Does that answer your question? Great.
Then we don't think about the remnant.
Now, remanence won't change the geometry. It'll change the local form, and it won't change the direction you're flying. Besides which, you don't know about remanence until later. Yeah, Elizabeth?
Yes, next one. It's from Sergio Espinosa Ivanhoe Mines from Vancouver. Another forgotten truth in mineral exploration seems to be anisotropy. For some reason, minerals geophysicists do not like to use the word anisotropy. Any comments?
This is from Sergio Espinosa in Vancouver. We all tend to ignore anisotropy because we're uncomfortable with it. And do I have any comments? Well, the most useful comment I can make is listen to what Ian McLeod has to say on the subject, because he said quite a lot lately. I think some of it to this audience. Am I right or not? Anisotropy turns out to be incredibly important, particularly in things like iron formation, but maybe in other places as well. And it's something we should be paying much more attention to than we have done up until now. I know Ian sounds like almost a broken record on the subject, but he has a message that we should all be hearing, and we should be modifying our practices. He's shown us the tools that will make a difference. Of course, he's selling them, but so far as I can tell, they're good tools. Now, I'm not a salesman for Geosoft. I work for the opposition.
Well, another one kind of reflects on Oasis montage. Peter Dalton says, so many positive and negative depth solutions given by Euler deconvolution in Oasis montage. What is depth, or what is height?
So who is the questioner from, sorry?
Peter Dalton.
Peter Dalton asked this question. We get both positive and negative depths from Euler deconvolution as in montage. Well, I take responsibility for the underlying algorithm in the Oasis montage implementation, but I don't take responsibility for the user interface. As a rule, you should get depths. If you get things going both ways, you've done something wrong. You've not got your gradients right, or you need to smooth your data a little or something. I think this is that's a discussion we maybe need to pursue offline. Email me some examples of things that bother you, and we'll see if we can sort out what's going on.
Non-geologic noise.
Okay, Dave Hatcher suggesting it could be non-geologic noise, and you're quite right, it could. But you should still be getting a dominant population that are depths that are down. I mean, we're not much interested in sources in the air.
Another question, Pedro Francisco says, I would like to know what causes a South Atlantic magnetic anomaly.
From Pedro Francisco, what causes the South Atlantic magnetic anomaly? Pedro, I regret I'm not familiar with what you're talking about. Is there a huge magnetic anomaly in the South Atlantic? If it's a regional one, my apologies for not knowing about it. But if it's in the South Atlantic, it's certainly not a mining problem. It's almost certainly something that's innate in the IGRF. And if that's not a good answer, my apologies. You've caught me out here. I don't really know what you're talking about.
Any questions? Next one. What is the total vector amplitude? Is it what we call total field anomaly? And this is from Abacoder, Abacoder.
Okay, Abacoder, okay, I know the gentleman concerned. What is this T that I've been talking about? If you take the number that you normally produce, the total, the magnetic anomaly, you can transform it into X, Y, and Z components and then add them together the way you add vectors together and take the length of that, and that thing is what I'm calling T. It's the length of the total magnetic vector. And you've got to use some Fourier transforms to calculate it. The description of what you do is in a paper by Petar Stavrev in Geophysical Prospecting about 5 or 10 years ago. And if anybody wants a reference, email me. Okay.
I recall your comment about not all the information's in the profiles, and one of the things I remember from the past in the petroleum industry in Calgary is they tended to they plotted profile maps in addition to the grid maps, and it's a hard product to produce because of the amplitudes and things, but it actually revealed a fair amount of information that you couldn't see in the actual grids at that time, or maybe the gridding algorithm have improved, but you could see some structure in the profile maps that you couldn't see in the grids.
Chris is making the point that if you do a profile map, you'll often see stuff in the profiles on the map that are hard to see in the grids. And of course he's right. I've used them myself to great effect, and I'm not suggesting you should not use it as a tool. I am suggesting if you go processing individual profiles, just remember whenever you process an individual profile and you're doing upward continuation, pole reduction, or any of these other things, you are assuming 2D extensions to infinity for that profile. And that may or may not be a good thing. The whole question of profiles instead of images was more important when we flew wider, because we weren't really sampling everything. More and more we're flying close enough that we can image properly, and really good mag surveys today do sample the field properly and therefore capture most of what there is to see. There will always be subtle things that are only in the profiles. So I'm not saying never use profiles, but I am saying if you use profiles and you process them as individual profiles, think about what you're doing. And remember, when you process a profile on its own, you're assuming 2D geology, and you might want to be thinking about what the filters are. Anytime you're using software that you haven't written yourself and you haven't thought about, there's tripwires waiting for you. You better understand what's going on. Otherwise, you're going to occasionally, maybe often, make some embarrassing mistakes.
Another question from Mahmoud Ahmed Abbas. He says, if geology is fractal, why the structural index not also be a real number?
Mahmoud Abbas is suggesting if geology is fractal, why should structural index not also be a real number? Mahmoud, that depends on how you define structural index, and the full answer is in the paper coming out in Geophysics, as I suggested. But the quick answer is if you define structural index by using homogeneity, then it has to be an integer. If you define structural index as just 1 over r to the n, and that n is just an index that you solve for and you accept that it's variable with distance and is not a constant of any particular anomaly, feel free to do what you like, because we're not then making any mathematically incorrect statements. If structure index is defined in terms of degree of homogeneity, it has to be an integer, or else you're dealing with a situation which is not homogeneous. And that arises because we're ignoring relevant parameters. The whole mathematics of fractals is poorly worked out, and I'm certainly not suggesting that the last word has been spoken on this subject, but I am suggesting that the free use of structure index in current software can get you into really messy places if you start using non-integer values. I can point to papers that are published in very credible refereed journals that produce totally erroneous results by using structure indexes that aren't integers and basically abusing commercial software again. I could go on at length on this subject, but I don't want to bore everybody. Are we done?
No. Another one. Akram Aziz says, is RTP applicable to archaeological prospecting?
Abraham Aziz says, is RTP applicable to archaeological prospecting? When you're doing archaeological work, you're almost always going to be dealing with remanence. This is a judgment call. Look at the anomaly, apply RTP, look at it again. Has it simplified the anomaly or not? If it simplified the anomaly, great. If it hasn't, it's because you've got remanence there. So I mean, this is a case of, by all means, use RTP, but keep your brain in gear. That's really the main message of this whole hour. Don't switch off because you've got a commercial product with you, no matter how high quality the commercial product. If you misuse it, it will mislead you. Any more?
Yes. We have lots of questions.
How are we on time? It's 5:30.
We have to have time to drink our beer that's been offered to us.
Yes, so is it time to wrap up?
I can send you the rest of the questions.
I'll happily respond to any more questions by email, but I won't respond for another week and a half because I won't be home until then. So by all means email me other questions, but expect a delay of a week and a half before you start seeing answers. Right.
Well, thank you very much. I'll make sure that you have the rest of the questions.